Hi everyone, good morning. I'm Shruti and in this video I'll be solving some Leetcode problems. It's been long since I resumed this because I was busy with my graduation, and I think it's the perfect and right time to get back on track and solve some problems which are different from previous. I'm also trying to maybe add more comments in previous videos with exact timestamps on what questions I solved earlier in earlier videos. But I'm excited to solve some more problems today, and thank you for joining me. Let's get started. Give me a minute. I should share my screen. Okay, the screen is visible, I suppose. Lead code question. Okay, so let's read this problem. This is 2096 step-by-step directions from a binary tree node to another. It's a medium problem. So let's read. You are given the root of a binary tree with n nodes. Each node is uniquely assigned a value from 1 to n. You are also given an integer start value representing the value of the start node s and a different integer destination value representing the node of the destination node. So we are given a root node. Each node is assigned value from 1 to n. We are also given integer called start value with start node s and a different destination value. Find the shortest path starting from node S and ending at node T. Generate step-by-step direction of such path as a string consisting of only the uppercase letters L, R, U. Each letter indicates a specific direction. L means go from a node to its left child node. R means go from a node to its right child node. U means go from a node to its parent node. We need to return the step-by-step direction of the shortest path from node S to node T. Let's read this example. So our route is 5, 1, 2, 3, null because there is nothing here, 6 and 4. And the start value which we have been given is 3 and destination value is 6. So we need to find the shortest path for from where I start from will be 3 and I need to end up at 6. So this is the shortest path it seems. So the output would be UURL because you are going to its parent node first. So its parent node is this. So U. And then its parent node, then again U. And then towards the right. So R. And then towards the left. So L. So the shortest path is 3, 1, 5, 2, 6. When it comes to two nodes like 2 and 1, start value is 2, destination value is 1. So you're just going left. That is why the output is left. So the shortest path is 2, 1. So let's write what all we know already. So I'm going to say we are given a binary tree where each node has a unique value from 1 to n. We need to find the shortest path from node S to node T. Then we can return the path as a string of, so L stands for go left, R stands for, I usually always write comments first because it's what I'm thinking I'm gonna explain to the interviewer, and this is what goes in when I first read the problem. So clarifying that does a big help, I think. Go up to a parent. So these are my three instructions, right? And let's think about the brute force now. What I can think of is building a parent map for every node. So tracking that, okay, this is my node and this is gonna be my parent. For this node, this is gonna be my parent. So make a map for every node. Then we can do breadth first search from starting to destination as well. So imagine you're physically like standing at a node S in the tree, but you have no map. And you are at a node S and you have three doors. You can either go to left door, right door, or the parent door, like back door. So you just try every possible path. Like you can go to one door, second door, and third door. And when you reach your destination, you just stop. So that is what BFS does. It explores like breadth-first search. It explores level by level. So from my current position S, I will try all the doors like left door, right door, and back door. From all those doors, I'll try these three moves again. Like again, I'll try from particular door, left door, right door, and back door. And I'll continue this until I reach my destination. The first time I reach my destination, that part is gonna be the shortest. But this is the brute force approach because to go up to the parent, I need to know which is my back door. So I need to do a full scan and reach every door from every particular door. So it's like lot of management, lot of work. So I'm gonna write this in easy words. Build a parent map for every node. Then use PFS breadth first search from start to end destination, traversing left, right, and parent edges. So they basically wait. Go to the next line. Yeah. I am just writing down my thought process. I'm at a node named S in a tree, but I don't have any map. I will try all possible paths from my current location. Can go to left child, or I can go to right child, or can go back to parent node. And stop when T comes. So basically from S, my current node, I will try all three moves, left, right, and parent. And then from each of those, this is not two, from S. Try all three moves again. Keep going until destination comes. Just like a train ride, right? I start from Bhilai or like my hometown, and then I want to go to Pune. So i'll wait I'll wait for all the steps. I don't think train ride is a good example though, because it's just linear, right? It's um but yeah, that was the analogy that came into my mind. So the first time I reach Pune, that's I know I have to end, and that's gonna be the shortest path. um so the first time I reach my destination, that is shortest in this case. So that is VFS concept basically. But here we need to do a full tree scan to know who the parent is and to build a map. Lot of work. This is like takes O of n square space. So not efficient. So another approach is finding a common route. Like, for railway networks, each train might go through Mumbai because it's like central place, or each train might go through Delhi because that's like the central hub. So each one of those will have like the central ancestor. So I think for optimal approach, the key insight is that the shortest path will always go through a common node, which is like the central hub. Go through the lowest common ancestor, or this is called LCA. So I can say the shortest path in any tree, in any tree, always comment always goes through the meeting point, or lowest common ancestor, and spelling ancestor. Yeah. um so I can go up from start to meeting point first, or LCA, and then go from LCA to destination. So this is what I can do. Start is like basically the route. Okay, so let me write down the algorithm and let's see. Algorithm. So my first step would be use depth first search from root to find path to start. So basically here first I'm going deep to the extreme node and then find the path to the root or root. So I wanna go from start to root. Now I know, okay, I need to take left and then left. So example, this is LL, move LL. Next is DFS from root to find path. Basically, this is my root, this is my meeting point, and this is my destination. So root, meeting point, destination. So now I'm from a path from root to destination. So here move is my right. I'm here, root, and I want to go to destination. So right and then left, RL. Strip the longest common prefix from both paths. Like cut off the shared beginning. But here we don't have a shared beginning, I think. Otherwise, we would have stripped that off. So I'm gonna replace whatever is on the left hand side, replace it with U. As we are going up that levels, right? So we are replacing it with parent. What is on the left with destination side? Keep it as it is. So here in this case, answer U multiplied by length of start path plus destination path. This is what I can think of. I never need to find explicitly the LCA node. No parent maps, no destination. There are just two clean DFS searches and some string trimming. Let's try to code it. So I have my class solution. I have a definition called getDirection, which takes the root, start value, and destination value. Like, okay. Alright. So I'm gonna create another definition called find path, which will take in a node, will have a target like the goal, and there will be a path. So what will we'll first write the base case, which is if we have gone past a leaf node, target is not down. So basically if there is not node, we return false. Then suppose if we found the target node or destination, path list as the full route, whatever list we passed. So we can say if node dot value is equal to target, then return true. So we'll try going left then right. For direct right. So I can write for direction comma child in left comma node dot left then right comma node dot right path dot append, go append that direction to the existing path direction. Take this step basically. Okay, if find path child comma target comma path, so we'll call that. If that is true, then return true. So basically we know target. Oh, why is this full stop? Why? Yeah. better now. Target, count down this branch, keep path. Otherwise, we'll do path dot pop. This is the dead end. Undo this step or backtrack. If this happens, we will in the end return false. Target not from if there's no target in any of the subtree. Either subtree. I'm gonna make two empty this say start path. This is gonna be a start path. It's gonna be a destination path. Now I'm gonna use depth first search from root to find the direction sequence to reach each node. Say find underscore path root comma start value comma start path. Left because if I'm at root 3 I'm gonna go left and then left for node 3. Then also same thing, but here this time it's gonna be destination path. So find path root, and here it's gonna be destination value and destination path. So this is gonna be RL for node 6. And then we're gonna strip the common prefix. These shared steps lead to the meeting point, or LCA, lowest common ancestor. This reminds me of another research that I read, that all of the people in the world, I don't know if it's true or not, I saw it in an Instagram post. It's like we all of the people and everyone nearby, we have a single common ancestor, which is a South African woman. So Google it and find more about it if it's true or not. We all have a common ancestor, which is a South African woman. Okay, I don't know if it's true or not, but might be. And that reminded me of this. Okay, everything before the fork point, same for both paths. So we skip it, go down and back up. I'm gonna say I equal to 0 while I is less than length of start path and I is less than length of destination path and start path of I equal to destination path of I, then do I equal to I plus 1 or I plus equal to 1. If this happens, if it's like, so we are incrementing, right? We are going to the next step. From start, go up. We are moving up one level, go up one level for each remaining step. From lowest common ancestor or the meeting point, which is 5, go down using remaining destination steps. So basically from here we are going up, from common meeting point we are going down until we reach destination. So we're gonna return u multiplied by length of start path minus 1 minus I Or a better way to write this is if I declare this as up moves and then this is not down moves. Then we're gonna return up moves plus down moves. So here the time complexity will be O of n, as we are using 2 DFS, 2 depth first search, each visit every node once. And for the space complexity, that is also gonna be O of n, because we have path arrays and recursion stack bounded by three heights, not three heights, three heights. So let's visualize one example. If my tree is, suppose this, right? And then my start, I know given to me is 3, and destination given to me in the problem statement is 6. So my step 1 would be calling find underscore path, this function basically. This will be called first. So if I call find path and I'm gonna pass root comma 3. So basically this is root node and this is 3. So this will, and my destination is 6, right? So this is gonna be destination 6. So automatically this will return, give me L comma L. Basically go left 1 and go left to 3. So these moves. Left to 5 actually. Yeah. Then step 2. Same thing, but here this will change. Root comma 6. So return right. So go right to 2. Go right to 2 and left to 6. Do we have any common prefix? I don't think so. There is no common prefix or anything here. Step 3. Common prefix. And as left is not equal to right. Step 4. Start leftovers. So from here I'm gonna go 2 steps up. Two steps up to become U. Destination leftovers. This becomes RL. Join both. Sorry. Start leftovers and destination. So our final string or answer will become UURL. So this is the whole walkthrough of all the explanation. Yeah, so what is the pattern here? Whenever pattern, whenever a problem asks for the path between two nodes in a tree, the answer runs through their LCA or meeting point. We explicitly don't need to find LCA node, stripping the common prefix of two root to node paths identifies it. Why not breadth first search? It can also work, but requires a parent map or code. Why replace with use? Because we don't know the exact edge directions going up from a node. But we know the number of steps to take. Okay, so okay, so I'm gonna try and run this. Says accepted, and then I'm gonna submit it. Okay. All right. taking a 2 minute break and then we'll start next question. I'm searching for my next one. I'm going to share my screen. Hope this is visible. Check. Yeah, it is. Um, okay, so let's read this problem. This is 1026 maximum difference between node and ancestor. It's a medium problem. Given the root of a binary tree, find the maximum value v for which there exist different nodes a and b, where v is a dot value minus b dot value and a is ancestor of b. What does being an ancestor mean? A node A is an ancestor of B if either any child of A is equal to B or any child of A is an ancestor of B. Didn't really understand that, so I'm gonna directly jump to the example. Okay, so this is our root and it has everything: 8, 3, 10, 1, 6, null, 14, um, null, 4, 7, 13. We have various ancestor node differences, some of which are given below. So here the output is 7. How? We have various ancestor node differences. So 8 minus 3 is 5. 3 minus 7 is 4. 4. 8 minus 1 is 7. 10 minus 3, 13 is 3. Among all possible differences, the maximum value of 7 is obtained by 8 minus 1 mod 7. So if you see at the node 8, the minimum we saw is 8 and the maximum is also 8. When we go down to 3, the minimum becomes 3 but the maximum is still 8. Okay, let's go down one more step. When we go to 1, then minimum becomes 1 and maximums become 8. So what is the difference? The maximum difference is my max is 8 but my minimum is 1. So 8 minus 1 is 7, which is like the largest number. So that is why the output is 7, because the difference here is huge. If I go down this path, the difference is just 4 because 3 minus 7. If I go down this path, the difference is 10 minus 13, which is 3. But the maximum difference we get is in this node. So that is why. The maximum difference in this case is here, because 3 minus 0 is 3, or here it's gonna be 1 minus 0, not that much though. That is why the output is 3. This is what I understood so far. Let's write what we have been given. We have a binary tree. We need to pick any two nodes where one is an ancestor of the other, meaning one is above another in the same path. the spelling ancestor, we need to find the biggest possible difference, that is top node minus bottom node. The brute force idea, the very simplest idea would be visit every node. For each node, walk all the way back up to the root, collecting every ancestor. So we'll visit each node. For each node, we'll walk all the way up, collecting every ancestor. And then for each ancestor, we compute ancestor.value minus node.value and track the maximum. But this will take O of n squared, as in every node we revoke the full path towards root, right? So now let's think of the optimal approach. As I'm going down any route, I'm passing the current node's value through all of its descendants, right? So if I'm at 8, then when I'm at 3, I'm also taking care of the 8, like while tracing back. So I just need to track the maximum at a node and the minimum at a node. As I said in previous example, I think, imagine the path from 8 to 1. So in the path we have 3 nodes, 8, 3 and 1, right? When I'm at position 8 or root node 8, the maximum I have seen so far is 8, as well as the minimum that I have seen is also 8. When I go down to 3, the maximum that I have seen is 8. It's stored in 8, but the minimum now becomes 3. As I go down to 1, the maximum I have seen so far is 8, but the minimum becomes 1. So basically what I am tracking is maximum of current node and also the minimum found so far while I'm on the path. So I'm tracking the minimum as well as the maximum. So here, instead of rechecking all the ancestors and going all the way back up, what I'm doing is I'm just tracking two numbers, minimum and maximum values seen so far from my path from top to bottom. So that I think might be the approach. Because I'm not like walking all the way back up just like in brute force, right? Let me try and write that. As I'm traveling down any route to I am passing the current node's value through all the descendants. The biggest difference is to track a minimum value and maximum value on a particular path. So I'm tracking simply track, how do we call, max of current node minus minimum so far, comma, maximum so far minus current node. So whichever among these is maximum among this or this, and then we pass to the max function. What I'm doing is, what I want to do is, instead of rechecking all the ancestors, I want to just carry two numbers, maximum and minimum values seen in every node. So far from path, so far from the path from node root to node. We can do this by depth first search, I think. Or one pass in one pass. So I have the definition called maximum ancestor difference, which has like root, tree node, all of this is passed. The output should be 7, and here the difference is the largest, 8 minus 1. So max is 8, minimum is 1, the largest difference is 7, so the output is 7. Let me create another function of DFS which will take node, track current minimum, track current maximum. If not node, leave parents already processed. Return the best difference seen. So I'm gonna return current max. Let me make this current max. Current max minus current min. So if I'm here, I'm gonna return current max minus current min. My current max is 8, my current min is 3. I'm gonna return the difference. Now I want to go down, and so I need to update the running minimum and maximum value, right? So I need to move out of the if. Update the running minimum and maximum with the node's value. Current minimum becomes the minimum of current minimum comma node dot value. Current maximum becomes maximum of current maximum or the node value. Now we're gonna apply recursion, like calling the same function, DFS function again. Recurs into both subtrees, pass updated maximum or minimum down. So I'm gonna write left equal to, I'm gonna call this function again DFS. And then what is my node? Towards the left, my node will be node dot left, right? Node dot left, and then current minimum for the minimum and current maximum for the maximum. I think. And for my right, it's gonna be DFS node dot right current minimum comma current maximum x. So this is updated here, and then we are passing the new ones to the left and right, and this happens all over again. And then finally I return the max of left of right. Return max of left right. Start with root value as both minimum and maximum. Gonna return DFS root comma root, because initially I wanna start with root dot value. It's minimum and maximum. So this approach is basically carrying minimum and maximum down. So let's imagine this one. So I'm gonna copy this part. I'm gonna do a walkthrough for myself. So my input is this, right? So step 1 will be path 8. So this is, let's not write step 1. Path 1 will be goes from 8, goes to 3, and then goes to 1, right? This path. So here in this case my minimum is 1 and maximum is 8. Difference is minimum minus minimum, which is 7. Next is my path 2, which can be from 8 to 3 to 6. Minimum is 3. Forgot to put comma. My maximum is still 8. Difference becomes 8 minus 3, which is 5. Path 3, which is actually here it should be 4 as well, because it's going down, right? Yeah. 8, 3, 6, and 7. In this case, my minimum is 3. Maximum is 8. Difference is 8 minus 3, similar as above, is 5. And similarly, there are so many paths that we can do from here, here, here. Path 4 is 8, 10, 14, and 13. Minimum is 8, maximum is 14. Difference is 14 minus 8, which is 6. So this is the visualization. Among all this, maximum value answered is 7, obtained by this, basically. So that is why output is 7. Now let's think about time and space complexity. What do you think? We are using recursion, so thinking it's gonna be O of n itself, and space complexity of h called stack, where h is tree height. Worst case on for a skewed tree, or O log n for balanced tree maybe. So what is the pattern here? This is carry state down DFS path. Give me a minute. Instead of storing the full history, I'm reducing it to minimum information needed. So yeah. Mm, it should be. I'm gonna try and run this. Okay, that's submitted. Okay, all right. Okay, 2-minute break again. It's my roommate's cat. You wanna go down? Okay, let me look for the next problem. Okay. I'll share my screen. Okay, so this is problem 1161 called maximum level sum of a binary tree. It is also a medium problem. Let's read the problem. Given the root of a binary tree, the level of its root is 1, the level of its children is 2, and so on. Return the smallest level x such that sum of all the values of nodes at level x is maximal. So suppose we have root with all the binary tree elements 1, 7, 0, 7 minus 8, null and null. Explain it. So the output is 2. How? Level 1 sum is just 1. Level 2 sum is 7 plus 0, 7. Level 3 sum is 7 plus minus 8, which is minus 1. So we return the level with the maximum sum, which is level 2, because 7 is larger than 1 or minus 1. So we are given a binary tree. We need to go level by level the tree and add up values at each level. Then we need to return the level number that has the biggest sum. If two levels die, return the smaller level number. So coming to the brute force idea, I think we can do, as we want to go level by level, we can think of using depth first search, record every node's values, and maybe keep it in a dictionary with like this level has this sum. So level and sum could be in a dictionary. Then we loop through all the levels and find the maximum of all the outputs or the sums. But this will take extra space as we are storing each values before calculating the sum, right? So this would be brute force, I think. Do a DFS, record every node's value along with its level into a dictionary. Then loop through all the levels and find which level has the maximum sum. Works fine but uses extra space to store all values before computing. Let's think of the optimal approach. At first search, Breadth first search is different from depth first search because in breadth first search we can still do level by level traversal, but we are gonna be using a queue. So at each level we will sum up all the nodes in current queue batch. We then track the best sum and best level seen so far. So we won't need a dictionary that way. We can compute the sum as we move along. Okay, so let's think about the code now. No collections, import dq, and we have a function maximum level sum, takes binary tree elements. So if not true, return 0. Then we can make a queue. D Q root level equal to 0. Current level counter will track the levels, number of levels, or the level number. Where sum is float, then this best level for the start we can keep to 0. So while q exists, we'll increment the level plus equal to 1, level underscore size equal to length of the queue. So we're gonna track how many nodes are at this level, and underscore sum equal to 0. Then we process exactly this level's nodes. So for underscore in range, level underscore size, node is q by we're gonna go at a particular level, count how many nodes are at this level, and then we're gonna process each level. Q dot pop left, then level underscore sum plus equal to node dot value. Then we check for the next level, nq children next level. So if node dot left is true, then q dot append node dot left. If node dot right is true, q dot append node dot right. Update based only on strictly greater. If underscore sum we declared best sum is infinity, then best sum becomes level underscore, by the way, minus infinity, not infinity. Underscore level equal to level. This should be near the value. So Let's do a walkthrough. So if we are at level 1, nodes processed would be just this one. Sum equal to 1. Best so far. Level equal to 1 and sum equal to 1. Level equal to 2, sum equal to 7. This is updated. Then level 3, 7 and minus 8. Sum is minus 1. But here, no update. As minus 1 is less than 7, right? So the answer is maximums level. Time complexity would be O of n. Node is visited once. Space complexity should be O of n. Skew holds at most one level at a time. BFS ordered traversal is the pattern here. Key trick is using length of queue at start of each spelling mistake. While loop iteration. To know how many nodes are at each level. Before adding children of the next level into the same queue. Oops. Okay. Okay, 2 minute break now. Song break, I guess. More than 2 minutes. Hmm. I'm listening to this song called Okay, done. Time to move to next problem. Oh shoot, laptops batteries. Charger cover. Alright. What? Okay, so this next problem is called cousins in binary tree. Let's read the problem statement. Given the root of a binary tree with unique values and the values of two different nodes of the tree x and y, return true if the nodes corresponding to the values x and y in the tree are cousins, or false otherwise. The two nodes of binary tree are cousins if they have same depth but with different parents. Note that in a binary tree, the root node is at depth 0 and the children of each depth k node are at depth k plus 1. If but not cousins. Two nodes they are at but have different parents. Return we need to return true only if both conditions. Brute force idea. When it comes to level by level, we can always look for like depth first search. So do a depth first search for each node. Set secretly to find its depth and parent. We can then store depth and parent for both x and y. Then check same depth and different parent and return true. Simple. This approach is simple but needs two full tree traversal. Think about optimal approach. Depth first search can be done separately. How about we think of breadth first search and check if two nodes have the same parent or different parents. If they have different parents, then they are cousins basically. Cousins. We can process parents, children if both x and y are children of the same parent. They are siblings. Not cousins, and we return false. So either use 2 DFS or use 1 BFS. 2 DFS is brute force. We can do BFS level by level. So can use BFS level by level. With this logic. From collections, import Q. Then I have a function called isCousins which takes the root as x and y. X and y are two different nodes of the tree, and all the elements of the binary tree are stored in the root. If not root, return false. Then q is dq root. While q exists, we'll take the length of the queue on the current nodes, level underscore size, length of queue, number of levels, or snapshot of current level, found x. Did we see x this level? Found y false. Did we see y at this level? So we'll then iteratively check for underscore in range, level underscore size, node equal to q dot pop left, just like in the earlier code that we solved before this. We are using pop left function. Then we need to check if they are siblings or have the same parent. Check if x and y are siblings, children of same parent. If they can never be cousins, right? So we return false. So I'm gonna say first I need to extract left value and right value. So node dot left equal to, or maybe left underscore value equal to node dot left dot value if node dot left exists, otherwise it's none. Similarly, extract the right value. So node dot left dot node dot right dot val if node dot right exists, else return none. If left underscore value equal to x, if left value is one number and right value is another number, and right value equal to y, or similar but swapped. I'm gonna copy this and paste here. Y and right value equal to x. Then we return false. This means they have same parents and are siblings. Otherwise, if left underscore value equal to x, or should it be y? Or right underscore value equal to x. If left and right both are maybe similar, then we found x. Semicolon. Similarly for y. Okay. If we found x and then we found y, we need to append it. Append node dot left, otherwise we'll append node dot right. If node dot right exists, if found x and found y, let's do a walkthrough. So let my tree be this, right? Now level 0. process root of 1. So the children of 1 are what? 2 and 3, right? Neither is x or y. Neither of them is x or y because x or y given to us are 5 and 4. So neither is x or y. So this, because of this, therefore found x becomes false. And found y also becomes false. Level 1. Process node of 2 and node of 3. So when next node 2 children are none and 4, right? Because none and 4. So I can say found for y equal to true, 4 equal to y. Not siblings with y. X. Node 3 children, none and 5. Found x true. The spelling here true. 5 equal to x. Not siblings with y. End of level. Because found x was also true and found both. Because both match this. Therefore, we return true. Coming to time complexity, I think it should be O of n. Each node is visited once. Space complexity should be O of w. Q is holding widest level. What is the pattern here? It is BFS level order with a parent-child pattern. So we need to check the sibling condition at the parent level, not at the child level. This will help us catch the same parent case without storing parent pointers. Here the spelling mistake, and here I forgot my underscore. I submitted. Run it first. Right. Okay, I think this is it for this video. I'll be solving more questions tomorrow, or let's see whenever. So I have some other projects to do now. But thank you for joining me in this video, and I appreciate you all. See you guys. Thank you for joining me in this video, and maybe I'll solve more questions tomorrow. Bye.